All right, let's get started. Remember that you have your first mini exam due on Monday, right? So hopefully by the time we finish today's lecture, you will have everything you need to take care of that exam, which really is just number 6. That's the only one that we haven't really talked about. All right, so let's continue where we left off. We were talking about the equation of a plane. And we said that we were not going to have a vector equation of a plane yet, that would come later. And that our standard equation for planes looks like this: ax plus by plus cz plus d equals 0. There, a, b, c, and d are all just numbers. And specifically, a, b, and c, if you write a, b, c in vector form as the vector a, b, c, then that gives you the direction vector of the normal vector to the plane, which is orthogonal to the plane. And that's where we ended. So we are going to start off by finding the equation of a plane through 3 points. All right, so how can we find the equation of a plane through 3 points? This is one of those fundamental skills you need to know how to do. Somebody provides you 3 points, you can find the equation of the plane through them. So you might want to put a little star next to this. That's a very typical type of problem that would appear somewhere on a test, an in-class test. Now it might be embedded in a bigger problem, but that skill has to be demonstrated. All right? So let me write down again the equation ax plus by plus cz plus d equals 0. That's the equation of a general plane. And here, a, b, c, that vector, if you take those coefficients of a, b, of x, y, and z, which is the a, b, c, and we call this vector n, then that's the normal vector for the plane. So that's the one that sticks out, that's orthogonal. So really, I just need to know what that point is, or what that vector is, and I also need a point. And the point can be any point on the plane. So maybe I should go back and just look at the notes. One more thing on the notes here. Here we go. This was it right here, this equation. See that? That's the equation we started with when I said this is the equation of a plane. And then I explained that when we reduce things down and simplify and get rid of parentheses, our final equation always looks like this. All right? So we want to get to here. All right? That's our goal, is to get to this using 2 pieces of information that we are going to need to determine. And then we will use that into this formula. So it's just kind of like a plug and chug problem. Once you figure out these missing pieces, you just plug things into the formula, and then we'll be done. So do we have a point on this plane? We need the normal vector, and we need a point. Do we have a point on the plane? Yes, right? We actually have 3 of them, don't we? So we get to pick any of them we want. So I'm just going to pick the first one, right? And I'll illustrate here. We need a point and a normal vector, right? That's what we need. So the point we've got covered. I can use the point 1, 2, 14. Check, got that. Now we need the normal vector. How are you going to get a vector that is orthogonal to the plane? Create 2 vectors from these points, cross those 2 vectors, and generate your normal vector. So visually, here's what we're doing. We have 3 points that live on a plane. We will generate 2 vectors, right? We will take those 2 vectors and cross product them. That will generate our normal vector, which should be orthogonal to both of those. So it's going to come out pointing perpendicular to the flat sheet of paper. Understand? Pretty good drawing? You're okay with that? All right. All right, so let's figure out how we're going to get these vectors. We've done this already, haven't we?
Yeah.
So we just label the points, and it doesn't matter how you label them. So I'm going to just label this one 1, 2, 14. Label this one -2, -5, -1. And why does it not matter how I'm labeling these? Like which is where? Why does it not matter? Yeah, but what I'm saying is when I draw 3 points in three-dimensional space, why am I not caring like where I put them? Does that bother you at all, or you're okay with it? Think about it this way. This might help. If I give you 3 points, let's say the camera is 1 point, let's say this green towel is another point, and let's say the corner of the room is a third point. Okay, how does that look to you? Like from your perspective, what does it look like? Well, it's going to depend on where you're looking from, right? If you're sitting over here, those points are going to look a certain way. If you're sitting over there, those points are going to look different, right? So when I draw 3 points in three-dimensional space, it doesn't matter where I put them because if you can imagine that you're looking at it from any perspective you want. That's why it doesn't matter. Now, when we draw on a two-dimensional plane, right, and I give you the point 2, 3, then 2, 3, this makes sense because there's really only one perspective we're looking at this from. We're all looking at it from the same perspective. Understand? That's why this doesn't matter. Now, how about in terms of the vectors? All I have is points right now. So what are the vectors? I labeled them this one and this one. Let's call them something. So how about u and v? So what would the vector u be? The sign-in sheet's coming around. Did everyone get it? No? Make sure you sign in for both Monday and today. Who needs it still? Right? Okay, so the vector u is the vector, what do you say? -3, -7. Everybody agree? Anybody disagree? I'm not even looking over there. Is this right? Okay. How about the vector v? 11, -5, -13. Anybody disagree? We're all good then? Okay, I'm going to take those, I'm going to cross them. When I cross them, I'm going to generate a normal vector. So the normal vector that I'm looking for is u cross v. Could I do v cross u instead? It'll give us an answer, but what's the difference between that one? It's a scalar multiple. So like let's say that this, if we cross u and v, actually right-hand rule, if I cross u and v, where's that vector n going to be actually? It's going to be down, right? Because right-hand rule. So n should technically be going down here. But it doesn't matter. If I do v cross u, I'm going to get the vector coming up like this. But the thing is, both of those vectors are orthogonal to the plane. Doesn't matter which side it's pointing from. All right? So that's not really relevant to us for this problem. All right, so let's do u cross v. And remember how I said when I do cross products, I like to write the two vectors and then just kind of like cover up columns. So if I'm going to get these three components, to get the first one, cover this up. Uh-oh. What is that? 91. So that first thing, determinant comes out to be 16 here? Okay. How about the middle one? Negative 204. And then 92. Okay, we'll trust those answers. That's just a cross product. You calculated it. We'll trust it. Unless somebody disagrees. Okay. Now, what? We have a point, and we have a vector that is orthogonal to the plane, right? So now we're going to go into this formula right here. Remember, this is A, this is B, and this is C. That's what that normal vector gives us. It gives us the coefficients that we're going to need. So let's plug in here. We have, using this equation, A, which is 16, x minus what? 1, right? I can use this, I'm using this point right here, and then plus b, which is negative 204, y minus 2, and then plus c, which is 92, and then z minus 14 equals 0, right? That is the equation of that plane. Any questions on where that came from?
So you can pick any point on that.
Any point, yeah. We could have used in here x plus 2, y plus 5, z plus 1.
And those will be your initial points for that equation.
That'll be, no, it'll give you the same equation.
Yeah.
It's kind of amazing that it'll do this, but if someone else were to have used a different point, then we would have got, let's say, 16. Let's do x plus 2, and then minus 204, y plus 5, and then plus 92, and then z plus 1 equals 0. What I'm saying to you right now is that these two are the same equations. Now, the only way to check it is to multiply through. So let's do this one. I'm going to need someone with a calculator. 16x minus 16 minus 204y plus what? 408 plus 92z, and then minus, what's this? 1288 equals 0. And let's get all our variables out here. 16x minus 204y. Meanwhile, somebody's adding up all those constants for me. 92z. And then you're putting in, right, minus 16 plus 408 minus 1288. Minus 896 equals 0. Good? All right, just to show you, this should give us the same thing. 16x plus 32 minus 204y minus, let's see, what's that? 1020, and then plus 92z, and then plus 92 equals 0. Put these constants together. All right? Yeah. 890 minus 896? Okay. And these are the same, right? These are the same coefficients on the x, y, z. So no matter what point we pick, we're going to get the same equation at the end. Questions? Yes?
So that negative 896 is like d.
Yeah, in the formula, that's d. So I'm glad you asked that question. If you go back up to the formula, right here, we should have some number times x plus some number times y plus some number times z plus some number by itself here, right? That for us, d here would be negative 896. Be careful, you have to pull the negative with it, right? Yes?
So that's how you want us to write our answers?
You should clean them up. Yes, you should distribute through your parentheses. That makes it a lot easier for me to grade, because then I don't have to check 3 different cases. I can just look at everyone's final answer. But it would technically not be wrong. I mean, this is the equation of the plane. It's just not simplified. All right.
So whenever we get into the equations of a plane, we don't want the 896. We want it to equal 0 and not equal.
I don't care if you would have moved the 896 to the other side. Yeah, that would be okay with me. Just to at least get rid of the parentheses. All right, so given 3 points, you can find the equation of the plane through them. All right, now the next thing that we want to discuss is if you have 2 planes, right? 2 planes, can we find the angle between them? I need some planes. I just happen to have 2 planes right here. So if I have 2 planes, let's start with this case. Let's say these planes are parallel, which means they do not intersect each other, right? What would the angle between the planes be?
0.
0
Or non-existent.
or 180 or non-existent? What makes sense to you? Let me do this. This might be easier. If I have two planes that hit like this, what's the angle between them? 90, right? 90 degrees. So these are orthogonal, aren't they? All right. What's the angle between them now? Is it getting bigger or smaller?
Bigger.
Bigger? Okay. And then when I get to this right here, right? What's this? What's the angle between them? 0, right? They're kind of pointed in the same direction. So what we want to do is we want to figure out, is there an easy way to figure out the angle between two planes? So do you think, is there something that you can think of that I could look at that would help me do this? The normal vectors. Okay, so each one of these planes has a normal vector, right? This has a normal vector, and this plane also has a normal vector. My planes are not going to hold up here, but these each have normal vectors, right? Come on, you can do it. These each have normal vectors. Did I start recording? Yes, I did. All right. These each have normal vectors. Look at what happens when they're orthogonal, right? When they're like this, when the planes are orthogonal to each other, look at what their normal vectors are. They're orthogonal also, aren't they? And then if I go like this, these two normal vectors are what? Parallel, and the planes are parallel. So when the planes are parallel, the normals should be parallel. And when the planes are orthogonal, the normals should be orthogonal. And then any other scenario, right, like if the planes are like tilted like this somehow, then the normals are going to be something, you know, maybe like this. And so really we're just interested in knowing the angle between these two vectors. If we know the angle between these two vectors, then we know the angle between the planes. And that's what this is saying. The angle between two planes is the same as the angle between their normal vectors. Now, I tried to do this with an animation here, but I don't know how. I think what I did here was outstanding, right? Compared to this. But I'll do it anyway. So you have their normals. See, I think it's harder to see here. And then, yeah, let's just move on. Okay, two planes are parallel if and only if their normal vectors are parallel. In other words, scalar multiples of one another. Two planes are perpendicular if and only if their normal vectors are orthogonal. In other words, the dot product of their normal vectors must be 0, right? That's how we check to see if vectors are orthogonal. So let's find the angle between these two planes. So what do you need in order to do this? I need to figure out what the normal vector is for each of those planes, right? That's what I need? So this is plane 1, plane 2. Here's the plane equation that I'm giving you. What's the normal vector of plane 1? 1, 1, 1. Now you're getting that from where? The coefficients of x, y, and z. Coefficient of 1, 1, and 1. All right. And then what's the normal vector for plane 2? So I'll call it n sub 2. 2, negative 4, 7? Okay. It's asking for the angle between these. So I know how to find the angle between two vectors. The angle between two vectors is the arc cosine of what? A dot B over magnitude of A, magnitude of B. In this case, since I'm using that notation over there, I'm going to dot the two normals, right? I'm going to dot the two, and then I'm going to divide by their lengths. And this will give me the angle between them. So what is the dot product? Let's continue this work here. Cosine inverse. What is the dot product of these two vectors? So you're doing multiplying, right? That times that, plus that times that, plus that times that. So 5? Just get 5. You're doing 2 minus 4 plus 7. So you get 5 on top. And then you need the magnitude of each of these. So what's the magnitude of n1? How long is this? So square root of 1 squared, 1 squared, 1 squared. So root 3. And then how about this one? What's the magnitude of n2? Root 4 plus 16 plus 49. Root 69. Yes? Okay. So we have root 3, root 69, and then just let's compute this on our calculators. And when you do this, make sure that you type it in correctly and make sure that you're in degree mode or radian, but you need to know what mode you're in. So I'd like the answer in degrees, just because I'm curious to know what the angle is. So anybody can volunteer that answer? What do you get?
24 degrees?
24? What do you get?
69.
You got 69 degrees?
69.66 degrees.
69? Anyone else?
I got 69 as well.
69 degrees, about, somewhere around there? Let's say approximately. Eric, double check yours. You might have had something go on there. Approximately 69 degrees?
I got the same thing.
69? Okay. So that is the angle between these two planes. Straightforward? I mean, everything we've done is pretty computational. I mean, it's pretty mechanical, right? You just apply the formula. All right, now, the line of intersection of two planes. This is really, really important. If you have two planes that intersect, okay? Because when you have two planes, they don't have to intersect, right? If they're parallel, they won't intersect. But if they're not parallel, then they have to intersect somewhere, right? Somewhere. They've got to hit each other. And where they hit each other forms a line, doesn't it? The line, you have a line of intersection. So visually, we have two planes that hit each other, and they have that bluish line of intersection, right? I would like us to figure out what the vector equation is of that line. In other words, you need to be able to give me an equation that would draw that line. Understand? When I say give me the vector equation of a line, that's basically saying give me the equation of that line. Like tell me exactly the properties of that line. Does that seem difficult? I give you two planes and you all of a sudden are going to be able to spit out the line.
Wouldn't you just find a line that's orthogonal of the two natural lines?
The two normals?
Yeah.
Yeah. What do we need for a line? Okay, first of all, let's talk about, make sure you remember, if we are looking for the line of intersection, right? What is it that you need to define a line using vectors? A direction vector and a point, right? If you can give me a point that's on the line and the direction the line points in, the direction vector, then we have the vector equation of the line, right? Yes? Okay, so here's how we're going to get that. To find vector equation of the line, we need a point and the direction vector. And I should not say I should say a direction vector, because it can be any vector that's pointing in the direction of the line. There's not a specific one, a scalar multiple of the direction vector. All right, here's how we're going to do it. How hard do you think it'll be for you to find a point of intersection? How hard do you think it'll be for you to find a point where the planes hit each other? Yeah, so each plane has an equation, right? Each plane would have an equation. All you'd have to do is find an x, a y, and a z that satisfy both at the same time. And we'll be able to do that pretty easily, as I'll show you in a demonstration. But the question is, how do we get the direction of this line? So how are we going to get a vector that points in that direction? And I think the easiest way to see it is to maybe, let me try it with my planes here first, and then I'll do it up there. So we have these two planes, right? And they hit at a line here. How can I find the direction of that line? So let's look at the normals, right? That's what was being suggested. Let's look at this normal vector of this plane, and let's look at the normal vector for this plane. They don't seem like they would really be connected to this direction vector, but they are. Can anybody see how they would be connected? Like what I can do with these?
Yeah, at the intersection of where they hit, wouldn't you use a cross product?
Okay, yeah, so imagine if I took these vectors, because I can slide these around. What if I put them both at the line of intersection, right there, and then cross them? That cross product would have to run in the same direction as that line. Now, I try and do the same thing up here. Let's see how it goes here. I'm going to, here are the normal vectors. So see the green vector? It's supposed to be orthogonal to the green plane. The orange vector is supposed to be orthogonal to that orangish plane. And since they're vectors, I'm going to move them around. So I'm going to move them so that they go both to the line of intersection. And I can do that because vectors can slide around, right? Then, if I cross them, see that red vector that popped out? That red vector is on that line. Okay, it's in that direction of that line. So that's how we will go about trying to find the vector equation of a line of intersection of two planes. So find the vector equation of the line of intersection of these planes. Now, are those the planes we just did? No. No, it's not. All right. So what do you need?
Yes, it is.
It is the same thing?
Yeah.
Okay, great. Wonderful. Let's start out with the let's try and find the point. So remember, we're trying to get a vector equation of a line. And we did that was it last class? A little bit in the last class, yeah. That's the general formula for the vector equation of a line, right? R naught really comes from a point, right? A point on the line. And then the V is the direction vector. So that's why I was saying we need to find these two things, a point on the line and a direction vector. I want to go after the point first. So for the point, can you give me a point that lives on both of those planes? How would you go about trying to find a point that lives on both of those? Do what? It's a system of equations. Well, you could do that, right? You could do a system of equations. What's wrong, though? You have how many equations? Two, and then you have three unknowns. So you're going to actually have infinitely many solutions to this. So we did this before. We actually were just kind of clever, and we just picked a value of one of the variables. We can just choose it. So why don't we just, for the sake of simplicity, why don't we just fix z to be 0? We could have said, let's let x be 0. We could have said, let's let y be 2. Let's let z be 10. We have some freedom here because there's an infinite number of solutions. So I'm going to just pick z to be 0. Why 0? Because it kills things off, right? If z is 0, then the first equation becomes x plus y is 5. And the second equation becomes 2x minus 4y is 10, if I move things around. And now we have two equations, two unknowns. And this we can solve by either substitution or elimination. This is something we would have done in college algebra. All right, so depending on your background, the way that I'm going to do it here I'm just going to multiply the top equation by 4. So multiply top equation by 4, I get 4x plus 4y equals 20. And then 2x minus 4y equals 10. I'm using elimination here. I'm about to eliminate a variable. Does this look familiar? Okay. I'm going to add straight down, and the y's are going to cancel. That's why I multiply by 4, right? So this gives me 6x equals 30. So x is 5. Now these numbers aren't always going to be nice, okay? But it works out that x is 5 here. Once I know what x is, then I can do what? Go get y, right? And how can I get y? Plug x equals 5 into either one. Doesn't matter. I'll go with the first one because it's the cleanest. So using that in this equation, I get x, x was 5, right? So 5 plus y is 5. So y must be, y is 0. So I have a point, don't I? It's the point 5, 0, 0. That point lives on both planes. The x is 5, y turned out to be 0, z started as 0, didn't it? You won't always get a point that lies on like an axis like this. I just got kind of lucky, I guess. All right, so point, check, we've got this. We're going to be able to come up with our R0. We're just going to use that turned into a vector. Then the direction vector. So to get the direction vector, v, what did we say we have to do? We're going to cross product of what though? The normals of each of the planes, right? I'm going to cross the normals of the planes. Right, each plane has a normal vector. I'm going to cross it. That'll give me a vector that's perpendicular to both, but that happens to lie in the same direction as the line. Yes?
How do you know the point we just found lies on the line that we're trying to find?
Because it satisfies both of these equations simultaneously. So look, if you plug in 5, 0, 0, you get 5, right? And now plug in 5, 0, 0, you would get 10, 0, 0, minus 10 is 0, right? So this point, well, where is it? It's gone. That point is on both planes at the same time, right? So it has to be on their intersection, which means it's on the line. But it's not the only point. Like, remember how I chose z was 0? You could redo this problem, let x be 0, and you would find a different point. So we all might have different answers depending on how we find that point. All right, let me cross these normals. What are the normals here? Normal of the first plane was 1, 1, 1. The normal of the second plane, I keep doing that, is 2, negative 4, 7. And we did cross those earlier or no?
Yeah.
We did?
That's fine.
This was,
That was a dot. 16.
it was a dot. Yeah, that was a dot. We have to cross these, so let's go ahead. Cover up this. 7 plus 4, right? 11. And then cover up this. We get 7 minus 2 is 5, but then change the sign to negative. Or change the sign. If it was positive, it goes negative. If it was negative, it would go positive. Cover up this. Negative 4 minus 6. So minus 6. So that vector right there should point in the same direction as our line. So we're ready. We'll come back over here. I'm going to write the vector equation of the line. R of t equals R0, which was any point on the line written as a vector. So this would be the vector 5, 0, 0, right? That's the one we found. Plus t times the direction vector, which was 11, negative 5, negative 6. If any of you have taken well, let me finish writing this first. This would be written together 5 plus 11t, 0 plus, so minus 5t, and then 0, and then take away 6t. right there. So that's combining them together. Again, we did that previous class. There's your vector equation for your line. Can we generate the point 500 with this? What would we let t be? If t was 0, we would actually spit out the point 500, right? But if you let t vary now and you let t be any real number, you're going to draw the entire line. All right. Good. Let's move on. All right, we're going to talk about two formulas now. They're both used to compute distances between things. Do we know how to find the distance between 2 points? We can, right? We have a distance formula. It works both for 2-dimensional and 3-dimensional points. We talked about the 3-dimensional distance formula kind of in the beginning of this class. I think it was the first day or so. But now we want to talk about some distances between things that are not as easy. Like the shortest distance between a point and a plane. Now, to me, this seems like a very tough question. So, like, if I asked you right now, what's the shortest distance between the camera and the floor? It would be the straight line down to the floor, right? Now, if the floor is the xy plane, then we're really just looking for the z coordinate, aren't we? The height would be the z coordinate of the camera, and that's easy to do because it's just one of the coordinates, right? If I ask you what's the distance between the camera and this plane, right here, the flat wall, then it would just be this coordinate, wouldn't it? But that's not interesting. How about the camera in this plane? You see, this plane's not one of our coordinate planes. So the distance, the shortest distance is not going to be just either the x, y, or z coordinate. It's going to be some shortest distance line that connects to that camera. That's a much more challenging problem. Do you see the difference? And that's what this allows us to do. So I'm going to show you first the geometric setup of it because there's a really good geometric interpretation of it. So we have some arbitrary plane, okay? It's just sitting there in arbitrary space. I'll even put a little tilt to it so you don't think it's one of the coordinate planes. Now, give me some random point. There it is. Some random point sitting in space, okay? There it is. I would like us to figure out the distance between that point and that plane, right? That's what we want. So here's how we do it, and it's brilliant. We just pick some random point on the plane, any point. We just pick it. Now, could you do that if I gave you a plane equation? That's a z. If I gave you a plane equation here, could you give me an x, y, z that satisfy this? You just have to think of one, right? Like how about 10, 0, 0? 10, this is all gone, that equals 10. 10, 0, 0 is a point on there, right? How about 0, 5, 0? Yes? So I can just sit here all day and give you points that live here. So it makes perfect sense that if someone hands me a point in a plane, and I'm trying to find the distance between them, that picking a point on the plane would be simple for me to do. All right? That's where we're going to start. We're going to pick some point, and then what we're going to do is we're going to construct a vector from that random point that I picked up to the, my code is wrong. That point should be on the plane. We'll do it like this so it looks like it is. Okay, so now what I've done is I've drawn a vector from that point, which is on the plane, up to this point, right? We're calling that vector B, but I'll get to that later. Now what I'm going to do is I'm going to show you a different vector. This is the normal vector for the plane. Now the normal vector, I drew it in a certain way. I drew that normal vector. That normal vector can slide around, right? But I drew it in a way that I wanted it to come up through this plane and go through that point, just so you could see some construction, some geometry starting to happen here. Every plane has a normal vector, right? Now what if that normal vector points in the other direction? It's okay because of what I'm about to do, all right? Just hang tight. I'm going to move the blue vector, because it's a vector that I drew from here. I'm going to move it so that it's attached to the tail of this vector. So I've got the tail of the normal attached to the tail of the vector that I came up with. And let me get the other vector out of there so it doesn't confuse you, all right? Now, that's what I want. That's supposed to be a right triangle.
So is it the same as like its projection?
Exactly. Do you remember the projection vector? Do you remember? You got up here and drew. Okay. So when we have a vector pointed in some direction, see this red one? We're not looking for the red one's length because we don't know how long this red one is, do we? This red vector could actually stop right there. It could go way up here. It could actually be pointed in the opposite direction. But it doesn't matter because we're projecting this vector onto this vector. And when we did that, it's okay if it's pointed over here. It'll just project down to here, won't it? And so this projection vector right here is the projection, right, of this blue one. I'm going to say the blue onto that red. Do you all agree? That vector. But that's not what we're interested in. We're not looking for the vector. We're looking for its what? Its length, which was called the component of the blue onto the red. Do you remember the difference between the two? The projection gave you a vector. The component gave you its length. So we're actually not even interested in the projection. We want the component of the blue onto the red. And what was the red vector? The red vector was the normal vector, right? And what was the blue vector? That's the one we came up with, right? We just picked a random point and created the vector that went from that point up to the point that we're interested in. If we can figure out the component of the blue onto the red, we have the distance, the minimum distance, shortest distance between the point and the plane. Yeah, and then we have to go back and look at the formula, but it's okay because I have it right here. Do y'all get this though? This is pretty awesome because if you did not have this idea of projections and vectors, to do this mechanically by hand would be extremely difficult to do. Like if you had no concept of vectors and projections, this would be a very hard computation. In fact, I'm not even sure I'd want to even go after it. It would be so difficult. All right. So let's see if these notes make sense now. Somebody gives you a point, x1, y1, z1, and they give you a plane that has an equation. We can find the shortest distance between them by first choosing any point on the plane. So that's that point that I would pick, right? I get to choose. And then we're going to create a vector from this point to the x1, y1. So that's the vector I create, and I'm going to call it b. Also, we have the normal vector, n. And then what we're going to do is we're going to do the component of b onto n. And when you do that, it would be n dot b magnitude or absolute value over the magnitude of n. That's the formula I'm going to use. This is the formula kind of if you plug everything in, but that to me that's cheating because you don't even have to think about it. It's just, this is what I would prefer you remember. If you're going to do the component of b onto n, you're going to dot the 2, get the absolute value of that, and then divide it by the length of n. Let's do an example. Find the shortest distance between these parallel planes. Now, how do you know that these are parallel?
Because the normal vectors are the scalar.
Yeah, the normal vectors for these planes are 1, 1, 1 and 2, 2, 2. And those are scalar multiples of one another. Therefore, they're parallel, right? What do you think the most common answer I get for this is that's completely wrong and doesn't require any work? What do you think the common answer for the shortest distance between these is? 15. That's what most people, like not most people, but most people who don't feel like thinking about it or weren't paying attention will just say, hey, if these are like parallel, then it should just be the difference between the 5 and the 20, and then it should just be 15. That's not at all what happens here, all right? Because these planes are tilted, okay? These planes have a tilt to them, so you can't just be looking at the difference of the constants there. All right. So,
How about just, because all we need is actually like one point in one of the planes, so how about just pick one of the planes and just choose one point and then measure the distance of that one point to the other plane?
okay, yeah, so you're telling me that the formula I gave you just a second ago got us the shortest distance between a point and a plane, right? But this problem is asking us for the shortest distance between a plane and a plane. It's not the same problem, or is it? I think that's what you're suggesting here.
Can we just choose any random point on either one of the planes and then just project it on one of their normal?
Yep, so y'all are thinking the same thing here. So in the previous, in what I just gave you, we started with the plane, and then we had some random point up here, right? But now, instead of this being a point, we have some other plane up here. And these are parallel planes, so I'll draw them like this. Wouldn't the shortest distance between these planes be the same as the shortest distance between any point on this plane and this plane? So we are going to first pick a point on one of the planes. And it's your choice. Let's pick a point on one of those planes. Let's call this plane 1 and plane 2 here. So you want to pick a point on plane 1? What do you want it to be? 500? Everyone good with that? Okay. Now, what we have is a point in a plane, and we're trying to find the shortest distance between these. So we're trying to find the shortest distance between these right here. Question, what is that? So we don't even need this plane anymore, do we? This plane up here, plane 1, the equation of it, I actually don't even care about anymore because all I needed that equation for was to grab a point. Once I have a point, shortest distance between this point and that plane, I follow the procedure now. So what is the procedure I follow? What do I do next? Find a random point on this plane. Your choice. 10, 0, 0? Good. Now, we're going to generate a vector, right? And that vector is going to go from the red up to the blue point. And this vector is going to be called vector B, right? That's what I used in the formula, B. That's our vector B. And what is vector B? Negative 5, 0, 0. Start putting this information here. Vector B is the vector negative 5, 0, 0. All right. What else do you need? You need one more thing. The normal vector of which plane? Yeah, it wouldn't actually matter because they're parallel planes, but following what we did in the previous note, it would be the normal vector of this plane. So what is the normal vector of this plane? 2, 2, 2. Right? All right, work it out. I want everyone writing and computing. I want everyone to get the same answer. Be right back. It shouldn't. Who has it? 2.88? Anybody else? 2.88? Yes? What do you get when you dot the 2? Negative 10, but then you take the absolute value. So negative 10, we're going to take the absolute value. And then what's the length of n? Root of 2, so 4 plus 4 plus 4, so root 12? Yeah. You got 4.33?
Negative 10 divided by 4 square root 3.
It's absolute negative 10.
Yeah, but you should still be getting 2.88. Oh, it's 2 root 3, not 4 root 3. You pulled the 4 out? Yeah, that's what it is. Okay, good? I don't know about you, but I think this is absolutely awesome. 2 arbitrary planes, shortest distance between them is a pretty simple computation, right? I mean, this is a pretty easy computation to do. I think it's great. Okay. Which, for a problem which would otherwise be very difficult to do. All right, here's another difficult problem, and it's the next formula. What is the shortest distance between a point and a line? So that is, I think, again, very challenging. If I give you a line sitting in arbitrary space, wherever, and I give you a point like the camera, and you're trying to find the shortest distance between this line and that camera, that seems like that would be challenging, right? In the same way that it was challenging for the plane. Almost seems like a Cal 1 optimization problem or something, right? But we're in 3-dimensional space, and we didn't do anything in 3-dimensional space in Cal 1, so we're kind of in a different world here now. All right, so let me show you the construction again. We have a point sitting in space, the camera, and we have a line. Now I said this could be tilted and that point can be anywhere, but if we kind of float around in the room and get to the correct viewing angle, do you agree that we could all get to a position where it looked like that to us, right? Yes? All right. So if we can get to that point where it looks like that to us, here's how we're going to do it. We're going to pick a random point on the line, and then we're going to pick another random point on the line, which, if we have the equation of a line, we should always be able to get 2 points if we want, right? So that should be very simple for us to do. And then we're going to create a vector, okay, and we're going to call that vector A. Now that vector A, couldn't that vector A also just be the direction vector of the line? Yes? Like if you actually know the direction vector of the line, then you don't have to pick 2 points because you already have a vector that would be parallel to A. So notice A is just some arbitrary vector that points in the same direction of the line. Then I'm going to construct a vector that goes from one of my points to the P. This is very similar to what we did before, right? Yes? Okay. Now let's look at the distance we're interested in. We want to know what that is, right? We'd like to know what this distance is. Now this vector goes all the way out here. So we don't necessarily have a right triangle or anything yet with Pythagorean. Do you agree? So you could look at maybe as a component, but see, we don't have a normal vector to work with. Remember in the previous problem we had that normal vector coming up and we were able to project onto it? We don't have a normal vector. The angle, well, I can tell you this. This is not obvious, okay? I don't expect anyone to see what we're going to do here because it's not an obvious result. It's something kind of like we make something appear that's not supposed to be there. Just hang tight. So do you agree with this construction so far? Okay, we want to know what D is. If we set up a right triangle like this, then do you agree with this statement that sine of theta is D over the magnitude of B? Okay, so I'm not even working with this side at all. Sine is going to be opposite over hypotenuse. B is a vector, but its length is the actual length here, isn't it? So do y'all agree with that? Pardon?
Would you use the cross product to find theta? Because it looks like B crossed with A equals the magnitude of B and the magnitude of A sine of theta, and then you just figure out what sine of theta is. And you go to find it.
Yes, we are going to use that, but we're not even going to have to work that hard.
Okay.
You're on the right track, for sure. Let me manipulate this a little more. Let me just multiply both sides by magnitude of B, all right? And then we have an equation for D, don't we? So if we multiply right now, both sides by magnitude of B, we got magnitude of B sine theta equals D. So in order to know what D is, I need to know the magnitude of B. Do you think you could tell me the length of this vector?
Yes.
I mean, because this point was given, right? And this point we picked. So I'm going to be able to find that length, no problem. The only difficulty here is finding perhaps what sine of theta is, because theta is the angle between these two vectors. So can you find the angle between two vectors? Yes, but that's going to require some work, right? However, if we remember this very, very cool thing, that if you take two vectors, let's say A cross B, and you take its magnitude, that's the magnitude of A times magnitude of B times sine of the angle between them, right? Remember that formula?
So can you just multiply both sides by magnitude of A?
We're going to almost do that. Not quite. Watch what we're going to do. This side right here almost looks like this, doesn't it? What is it missing? Magnitude of A, right? So watch what I'm going to do. I'm going to multiply by magnitude of A and divide by magnitude of A. And now, isn't that numerator, that cross product? And the denominator is just now part of our formula. We are realizing a hidden 1 right here. Again, I wouldn't expect you to see that. Okay, someone else saw that already for you. And I'm just here to show you what they saw. All right, so I didn't see it either. All right. Okay, so that's pretty awesome, right? We want to know what D was. D was almost this. It was missing the magnitude of A. We insert it properly, and now the formula becomes D is equal to, it's the cross product of A and B, magnitude, divided by the magnitude of A. Again, a very, very clean computation. There are two things we'll need to know, right? We're going to need to know what the A vector is, and we're going to need to know what that B vector is. But the B vector, we generate that. We get to pick it. So this is going to be cool. All right, got it?
Either equation we can use.
Either, what do you mean either one? Like this one? Mm-hmm. Well, what's the big difference between these two equations?
Well, that one you don't need the angle?
You need the angle here, right? You need the angle. And for this one, you don't. This cross product magnitude has no angle involved at all. This is a much easier computation than this computation. See that? Math can be so beautiful sometimes. I mean, just the fact that it works out that way. All right, find the shortest distance between 3, 6, negative 7 and the line through these 2 points. So I give you a point, and then I give you 2 other points, and there's a line between those 2 points. So let me draw the picture. And it doesn't matter how I orient things, right? Because I could be sitting anywhere in arbitrary space here. I'm trying to find the shortest distance between this point and the line that connects these 2 points. And according to the formula that we just derived, kind of, what are the 2 pieces of information I need? What are the 2 things I need? 2 vectors. Which ones are they?
So one on the line and then from one point on
Okay, so one of them is going to be a vector that's on